Hello, everyone. The topic for our project is feature-driven anomaly detection in UAV GPS spoofing, and our team members are Amit Samant, Apurv Anand, and myself, Akash Kotak. Next slide, please. Yeah. So we have real-time anomaly detection in wireless sensor networks using machine learning. We have done the integrity and reliability of data collection by wireless sensor networks, which are critical. This paper represents a research project focused on developing and evaluating machine learning-based anomaly detection techniques for real-time WSN applications. We also explore the efficacy of random forest support vector machines and deep learning architectures tailored for WSNs. Our aim is to create a robust and energy-efficient solution capable of identifying anomalies in sensor data streams in real time. Next slide, please. Coming to the introduction, the proliferation of WSNs has revolutionized various fields, including environmental monitoring, industrial automation, and healthcare. These networks rely on distributed sensors collecting and transmitting data, enabling real-time insights and informed decision-making. However, the integrity and reliability of collected data are paramount, particularly in critical applications. Anomalies such as sensor malfunctions, cyber attacks, and environmental disturbances can significantly compromise data quality and lead to erroneous conclusions. Real-time anomaly detection plays a crucial role in safeguarding WSN data. This paper represents our research project on developing and evaluating ML-based techniques for real-time anomaly detection in WSNs. Now, coming to the literature survey part. Existing approaches to anomaly detection in WSN often rely on statistical methods such as outlier detection and change point analysis. Distance-based methods like the k-nearest neighbors, employee reference models, or clusters to identify anomalies by comparing sensor readings. And recent research has witnessed a surge in ML-based anomaly detection techniques, each holding a unique key to unlock the mysterious ways of WSN data. Support vector machines with their robust classification capabilities have been employed to effectively separate normal data from anomalies by mapping them into a high-dimensional space. However, the optimal kernel selection and hyperparameter tuning can pose significant challenges. The random forest, on the other hand, has gained traction due to its ensemble learning approach, combining multiple decision trees to reduce overfitting and handle mixed data types with ease. While offering interpretable results, the RF's performance can be swayed by feature selection and the number of trees employed. Next slide, please. Our approach includes the exploration of 3 ML models: random forest, SVM, and deep learning architectures. And we implemented a modular and scalable system designed for real-time anomaly detection on resource-constrained WSN nodes. And the use for dynamic selection and fusion techniques to adapt the ever-evolving data characteristics and attack types are going to be discussed in our future approach. Next slide, please. Now, I would like to hand over the presentation to Amit.
So our report delves into the UAV network communication experimental dataset. This is the information about dataset as it is a treasure trove of network traffic captured from unmanned aerial vehicles, UAVs, during a simulated search and rescue mission. It goes beyond the mundane, encompassing both legitimate communication and the insidious whispers of Wi-Fi and GPS attacks. The dataset captures two main types of attacks: Wi-Fi attacks. These sneaky maneuvers aim to disrupt the UAV's communication with their ground control. Imagine the attacker sending forced deauthentication packets, essentially acting like a digital bouncer, kicking legitimate users off the network. And the other ones is GPS attacks. These aim to cripple the UAV sense of direction. One way is through jamming, where the attacker blasts a signal on the same frequency as the GPS, effectively drowning out the real signal with the static. The dataset is a goldmine for researchers in two crucial areas: intrusion detection systems, IDS, which can be built a powered system that can sniff out these attacks in real time before they cause real damage. Researchers can use the dataset to train and test their IDS, making them smarter and more vigilant. countermeasures to how can we make UAV networks more resilient against these attacks. The dataset provides a platform to develop and evaluate new techniques like encryption, signal authentication, and anti-jamming technologies. By understanding how attackers operate in the simulated environment, researchers can develop the tools and techniques to keep real-world UAVs safe and their missions on track. Here I'll be discussing the machine learning models which we use to implement our theories and analysis. The first one is the statistical models which were used are naive-Bayes model. Naive-Bayes model excels at handling high-dimensional database with mixed types, and like sensor readings, analyzing probabilities to identify anomalies. It is efficient, requires minimal configuration, and sets a solid baseline for comparison. The second models are supervised learning models. Here we are using support vector machines SVMs as it is a robust classifier. It's like a skill swordsman, mapping data points into a high dimensional space and then slicing through them with the perfect hyperplane to separate anomalies from normal data. We will explore various SVM kernels to find the best fit for our dataset. The other one is random forest. Random forest combines multiple trees to reduce overfitting and boost accuracy. It is versatile, handles mixed data, and helps us understand which features are most important to anomaly detection. Then we have gradient boosting. Gradient boosting iteratively builds upon weak learners, refining predictions like a sculptor shaping clay. This makes it ideal for capturing intricate anomaly patterns and handling complex interactions and noise. The next one is logistic regression. The logistic regression is efficient for large data sets and excels in binary classification, making it perfect for our goals. The comparison metrics that we have used here are accuracy which provides us with the overall percentage of correctly classified instances, which is a general score of how often the model gets it right. The second one is precision, which is the ratio of true positives, correctly identified anomalies to predicted positives. All instances the model flagged as anomalies. This indicates how rarely the model scries both or like it gives out a wrong anomaly. Like if an anomaly is not an anomaly and it's giving as an anomaly, that's what it is. Then we are evaluating it on based on their recall value, which is the ratio of true positives to actual positives. Total number of anomalies present. It measures the model's ability to capture all anomalies. Then we have the last one, the last matrix is F1 score, which combines all precision and recall into a simple harmonic mean. It balances catching real anomalies, recall, and avoiding unnecessary alarms, which is completed in precision. Then other models use logistic regression. It's efficient for large data set and binary classification, suitable for simple spoofing patterns. Data decision trees it is easy to understand and visualize decision rules, but prone to overfitting and noise. Then we have K nearest neighbors, KNN. It classifies data based on majority votes of its neighbors, adaptive to new data and complex boundaries, but it is sensitive to scaling and dimensionality. Then we're using neural networks, which is highly flexible and capable of learning complex relationships, potentially leading to a superior anomaly detection, but can be black box and it requires careful tuning. Then we have convolutional neural networks, CNN, which is efficient for time series data like sensor readings, and it is able to capture localized anomalies within any network. Then we have long short-term memory, LSTM, which is a recurrent neural network and it specializes in learning temporal dependencies, and it is ideal for detecting anomalies that evolve over time. Now, the comparison process that which we use with all these models are that all the models were trained on the same data set and divided into training, validation, and testing sets. Then features were extracted from the data sets and were used as input for each model. Here, feature extraction and normalization of the data set took place. Then we have different parameter combinations which were explored for each model to optimize performance. Like we wanted best accuracy and recall values so that we can get the best result. The models were then evaluated on testing set using the 4 metrics which were mentioned in the last slide. The results were then compared to identify the best performing models for anomaly detection in a specific scenario for the UAV dataset. Now we go to key findings, which will be continued by Apoorv.
Thank you, Amit. So, one of the key findings, we start off with how neural networks and convolution neural networks achieve the highest accuracy and F1 scores, indicating their potential for superior anomaly detection. Random forest and gradient boosting offered a good balance between performance and interpretability, making them potentially suitable for real-time applications. Simpler models like naive Bayes and logistic regression performed moderately, suggesting their possible use for initial anomaly detection or constrained environments. Decision trees and k-nearest neighbors exhibited lower performance overall, highlighting their limitations for complex spoofing detection. Next slide. Okay, so here's the data that we collected right after training all these different models. So let's start with the first one, that's naive Bayes. We see all the four evaluation metrics that we're using, and we come to the conclusion for naive Bayes is that its strength is that it's easy to implement and efficient, whereas its weakness would be it assumes feature independence. For SVM, its strength is it's powerful, non-linear, but and robust to outliers. But its weaknesses would be like the parameter tuning is challenging. For random forest, its strengths were it handles mixed features. It gets the right stuff and the important scores. The weakness would be computationally expensive. For gradient boosting, the strengths were it's highly accurate and flexible, but its weakness was it's susceptible to overfitting. For logistic regression, its strengths were that it's easy to interpret and efficient, but the weakness is that it assumes a linear relationship. For decision trees, the strength was that it was easy to understand, prone to overfitting, but the weakness was it was prone to overfitting and had and noisy data. For k-nearest neighbor, its strength was that it's simple and robust to outliers, but its weaknesses were that it was sensitive to scaling and dimensionality curves. For neural networks, strengths was it was highly flexible, but its weakness was like it requires large data sets and it might be prone to overfitting. CNNs were efficient for time series auto feature extraction, but the weakness we found out was like it requires large data sets and is sensitive to hyperparameters. The long short-term memory (LSTM) and recurrent neural networks showed that its strengths were that it captures temporal dependencies, and its weaknesses was that it was computationally expensive, needed careful design and tuning. Here we have a graph of all the values that we got, the accuracy, precision, recall, and the F1 score. So we can, analyze and compare all these different models on the same plane. Next slide. All right, now let's come to the discussions. The extracted features provided a solid foundation for all models, with complex models like neural networks and CNNs achieving the highest accuracy in F1 scores. The random forest and gradient boosting offers a good balance between performance and interpretability. Simpler models like naive Bayes and logistic regression perform moderately, potentially suitable for initial anomaly detection or resource-constrained environments. Now talking about a future trajectory, future works that can be done on this. Firstly, enhance features, integrate flight path and environmental data for richer anomaly detection context. The second thing that we're thinking of is ensemble training. That's where we combine the strengths of multiple models for potentially superior performance. The third one is unveiling the black box, develop interpretability models, methods for complex models like neural networks to understand their decision-making process. And the fourth one is real-world deployment, implement the trained models for continuous anomaly detection and spoofing mitigation in real-time UAV data streams. And in conclusion, so we implemented ML models powered by extracted features, showed promising potential for GPS spoofing detection. Further research and refinement can unlock robust and interpretable solutions, safeguarding UAV operations. Key takeaway from this research was that machine learning shines in identifying anomalies, indicative of GPS spoofing, feature engineering plays a crucial role in boosting model performance. If you go through our paper, you'll see the process that we've used for feature engineering, and making sure the IPs have context where they can be used as a feature. And the call to action here is invest in further research to unlock the full potential of ML-based anomaly detection for UAVs, and prioritize interpretability to build trust and transparency in anomaly detection systems. That's it. Thank you.